We have been studying how to implement CDCL with a theory. Theory can be anything, and we have seen algorithms for QF, EUF, and in those algorithms we are maintaining equivalence classes and merging them and separating them based on push and pop in the CDCL level. So now we will look at how to implement those algorithms efficiently. So there is an algorithm called union find, which is pretty standard for implementing equivalence classes, and that is very useful also in the context of SMT solver. First we will look at a standard implementation, and then we will see in later sections that how to adopt it for the purposes of SMT solver. So equivalence classes are usually implemented using union find data structure. Each class is represented by a tree over the member terms. Okay, so you have terms, and you make a tree which connects them, and this is your equivalence class. The root of the tree represents the class. There will be a term which will be sitting at the root, and we will call it as a representative of the class. The get class, if you give it a term and ask me that what is the class of this function, it will return a root of the tree. Okay? And which involves traversing to the root. Right? So if you we will see how this traversal happens. Merge classes. If you express equality between two terms, you go and pick up their corresponding classes and try to merge them. What we do is simply add the root of the smaller tree as a child of the root of the larger class, and you take two trees and merge them and make one tree. The important bit is the root of the smaller tree become a child of the root of the bigger tree. It is considered to be very efficient data structure, and after n equality pushes, on an average you will have a performance of n log n. Let us look at an example how this data structure will proceed. We have 8 equalities, and then it ends with the last inequality. So first we have an equality T1 equals to T8. So we will create a equivalence class which will consist of two nodes, T8 and T1, and we will arbitrarily choose one of them as our root node. Let's call it T8, and we will connect one T1 to T8 via an edge, okay, and label it with which equality is causing this equivalence class. Now the next one is T7 equals to T2. Again, this is new set of terms, so we will create another equivalence class where the root is T2. Now I am making T7 equals to T1. The T7 is here and the T1 is here. That implies that these two equivalence classes has to be merged. So how do we do it? We pick the root of a smaller tree. You can see that their sizes are same, so therefore you can choose arbitrarily any of them. So let's choose this guy and connect it to T8. Now let's move on and let's add T6 equal to T7. T6 is a new term, and the T7 is a term which already in a sum class. So we create a node called T6 and call it its own equivalence class. Then you can see that this equivalence class has larger number of nodes. Therefore I will connect T6 to T8 and label it with 4. In the next step you can see that that's what we did. Now let's process T9 equals to T3. You can see that there is no 9 and 3 in this whole set, so you create a completely different equivalence class pair, T3 T9, and connect it via 5. Now you say T5 equals to T4, you do the same thing again, and you connect T4 and T5. Now again I say T4 equals to T3. Once I do T4 is equal to T3, what's happening, right? Again we have ambiguity between these two guys, T3 and T4. They are the roots of the equivalence classes, but their sizes are same. So you choose arbitrarily one of them. I connect like this. We are labeled by 7. Now let's continue, and last equality is T7 equal to T5. The T7 is here and the T5 is here. Now I want to say that T7 equal to T5. So we go and pick up their respective roots, which is T8, and the respective root of T5 is T3, and which one has a smaller number of nodes. So T3 has 4 nodes, T3 has 4 nodes, and T8 has 1, 2, 3, 4, 5 nodes. So this is a bigger class, so therefore I will connect it like this and label with the H. Now if I say T1 equals to not equals to T4, it's not possible, because if you look at from T1 to T4 there is a path. Yeah, you interpreted undirected graph, so you can, there is a connection, they belong to same equivalence class, therefore you can say that they have contradiction. So once we have this even infinite data structure, you can add equalities and disequalities and create these trees. But what about computing unsatCore? So how do we get unsatCore out of such a tree? That question is important because we need to produce a clause back to our CDCL level, such that we can introduce a conflict clause from our contradiction. We generate the proof from our data structure, which proves the satisfiability of the formula, and the leaves of that proof is our unsatCore. So how do we generate the proof? So first of all, there must be some disequality that must have been involved in the producing the contradiction, right? That's how it happens. Things become equal and somebody saying no, you cannot make them equal. So that collect that equality, that will be important. Okay? And some other set of equalities must be causing S equals to V. Let's try to find those which cause S equals to V. How do we find those? Find the node S and V which are in your tree, and look at the path from S to V. Okay? And from the path S to V, you find the edge which was added latest, and that edge is the edge that caused these two guys to come into the same equivalence class, and that edge is part of your proof. So T equals to U is causing U S and V to join into same equivalence class. So now you want to figure out who caused T equals to U. Probably you added because of its input, and you want to also figure out who made these guys equal. Means what makes T, S and T equal and U and V equal, and we search for these proofs recursively. At some point of time you will find that all this recursion end up one single edges where you have a label which equality made it happen, and there you have leaves. Yes. Right. So let's look at in our example how this works. So we had this set of equalities and a one disequality, and we had a contradiction, and we had created this tree to represent our equivalence class, and it is saying T is not equal to T4. So clearly T1 is not equal to T4, part of your proof, and somebody contradicted it. So what contradicts T1 not equals to T4? T1 equals to T4. So let's see who brought T1 and T4 into same equivalence class. You just look at T1 and T4, draw the path, and the latest edge is 8. So 8 is causing T1 and T4 to join same equivalence class. So what is the equality 8? Equality 8 is T7 equals to T5. You write it in your proof, T7 equal to T5. Now I need to find out what makes T1 and T7 equal, what T4 and T5 equal. So if you look, T1 and T7 are here, and T5 and T4 are here. Okay? So let's continue, and 3 is the latest edge, 3. Okay? That brought T1 and T7 in same equivalence class. Okay, and you go and check, okay, what is my third edge, and it was T7 equals to T1. Oh, you found it. So I was looking for who made T1 equals to say T7, and that was T7 equals to T1. So therefore you can apply symmetry and you get T1 equals to T7. Now what this one more thing is left to do is to find what made T5 equals to T4. So look at T5 and T4 was here, and there's a path where has exactly single edge 6, and which was appearing here. This is T5 equals T4, and you can write it directly there. So this becomes a valid proof in the theory of equality, and it has 3 leaves. This guy, this guy, this guy. Actually there are 4 leaves, and if you put them together, it becomes an unsatCore of the whole formula. And now we can send it out, send it back. Negation of this unsatCore would be a concrete clause for the CDCL level. This is not it. We have another issue on top, which is congruence computation on top of this equality reasoning. So how do we incorporate that in our union find? So when we construct nodes in a formula, for example, in this formula you have f to the power 5a equals to a, f power 3a equals to a, and fa not equals to a. So among all the nodes, you create this parent relation. It tells you what is this node or who is the child on this node. And once you draw this parent relation, then you can apply congruence whenever you have things become equal. First, what we do is we draw the edges as we have been doing edges for union find. So first edge comes from f5a equals to a. So you draw this edge. Now f3a equals to a. So f3 is joining this group, but the thing is this guy has only one member in his equivalence class, and this guy has 2 members in his equivalence class. Therefore, this guy wins as a root, and you will connect these 2. Yeah, that's what we do. We have to construct this inequality. You can see that this inequality, these 2 guys are not in same equivalence class. You may say it's a satisfiable, but it is not. Okay, so you need to still apply the congruence closure. Congruence closure is what? When 2 things become equivalent, you need to say that their parent is also equivalent. So you can see that f to the power 3 is equivalent to the f to the power 0, right? So their parent, these 2 guys, should also become equivalent. So you should supposed to draw this edge. So you can say that if I apply congruence on 2, I get this edge. Now we carry on and we ask ourselves, can we apply more congruence? Yes, we can further. These 2 guys has become equivalent. So I can say, oh, these 2 guys, their parents also can be equivalent. But this guy is a member of this equivalence class. So when this guy will join the equivalence class, it will join this node. Yes. So we create an as this, and then we'll say we apply congruence on congruence, and then we got this edge. This keeps the record why we did something. Now we can continue this example, and you apply one more congruence. You will find that this guy will also join this equivalence class. Try to figure it out. How do we apply that congruence? One more thing to think about is, from this kind of graph, how do we learn the proof of the data structure? Because now things are not just simply labeled by the equality, it is labeled by congruence on some equality. So from that we need to put extra work to figure out what is the proof of contradiction.